Okay, I continue with the week 5 topic, which is the second part of the engineering application of vector algebra. But now we look in the class I already go into 5.1, which is the application of vector algebra. Now we look into the vector analysis. Normally the application of vector analysis involve navigation. Navigation. So why is that? Because the navigation problems is not just the direction, it involves the magnitude as well. So from the understanding that we have from the vector analysis, where we know the magnitude and also the direction of the vector, we can determine the resultant forces or the resultant location of the problem in hand. So we can use head to tail method that we already covered in the week 3 classes, where we can get the resultant forces based on the head to tail method, where we combine the initial point to the terminal point. Okay, all right. Now the concept of that vector analysis is being used on the navigation, where in summary, if I can put it this way, where the course is actually the direction of the line drawn, and heading meaning that the terminal point that we are going into that direction, and the drift angle is the angle between heading and the track, a speed, ground speed, and so on. So this is the terminology that we're being used in the navigation system. But then again, it depends on whether the navigation on airplane navigation, the car navigation, and so on. Okay, so for example, as given in this example 5.3, a jet airliner is flying due east. So this is the east direction, where it flying due east. However, when the jet is flying with the 500 mph, mile per hour, it encounter the 70 mile per hour tailwind blowing in the direction of 60 degree north, so north of east. So this is how it looks like. So it this way, this way, and the remaining is 30 because it's the total is 90 degrees. So the airplane holds its compass heading due east, but because of the wind, acquire a new ground speed and direction. So what are they? So this is the classic head to tail problem, that we can solve using this method. Okay, all right. If you look at the solution is available at the next page. So we are dealing with two vector here. The first vector is the vector that the airliner try to fly at first, which is in this direction, in x direction. So the u is actually with the 500 magnitude, 500 at the I direction, but nothing at the y direction. Okay, and also we do have the vector v, that coming in this way. So this is 60 degrees, and the component of this vector in terms of I and j can be arranged in a manner like this. If I can redraw, this is the vector, this is the 60 degrees, this is the vector. So we need this component, the j component, and we need this component of I component. So the I here is actually the vector v cos 60 degrees, because it's here, and here is v sin 60 degrees. You use Pythagoras theorem because the total here is 90 degrees. Okay, so in the I direction is vector v cos 60 degrees, and then the magnitude of v in 60 degrees. Okay, here. So the magnitude is 70 just now. 70 cos 60, another one 70 sin 60. That is for the v. Or if you can change it, it become 35 like this, because this one you get half, and then here you get 35 third 3. Alright, and that we need to find u plus v. So we can do it this way, and we can do it head to tail method as well. So u plus v, u is this one plus with this one. So 500 plus 35, and then 0 plus 35 third 3. So you will get 535, and then 35 third 3 in J. And its magnitude is this one lah. 535 squared plus 35 squared 3 squared. Okay, here you will get about 538.4. And the angle, they ask you what are the speed and the direction. So this is the speed, and the direction is just tangent inverse the y component divided by the x component, which is 35 square root of 3 divided by 535. So that's why you get about 6.5 degree. So this is how you get the solution. Okay, all right. Next, we have this example where example 5.4. Hold on, example 5.4. Okay, we have two string like this. One in F1 direction, another one is in F2 direction, and then we have the mass here. Almost similar like example 5. Example in the beginning of 5.1. So we have the weight going down of that 75, and then there must be the force upward as well, and then there's a tension of this F1 and also F2 here. Okay, all right. So the F1 here, and then the angle here is 35. Okay, and then the angle here is 40. So looking at this, the F1 is actually in the y direction, in the x direction and y direction. X direction is negative I direction. This is positive I direction, right? So you get negative F1. F1 is the magnitude, and then cos 55 because you want this area. And here will be F, the magnitude of F, sine 55. For the F2, now is the I direction, and that's why it's positive. F2, the magnitude of F2, cosine 40, and then at the y direction, F2 sine 40. Alright, so the summation of it is actually F1 plus F2. If you move here, and then F1 you can replicate here because it's parallel to this one. It will have the same direction and also same magnitude. So the resultant is in the middle, which is the force here, which is equivalent to 0 and 0 in y, and then 75 in the direction. Okay, so the resultant force of this at the x direction and also y direction. This is x direction 0. This is the y direction, x direction. So from here you can, because you got two linear equation already now, so you can solve what is the F and also what is the F2. So from here that you get the F1 is 57.67 Newton and F2 is 43.18. So therefore the F1 vector is given as the magnitude of F1 57.67 multiplied with cos 55, so that you get this one. Okay, same goes with the rest of the coordinate like this. Magnitude of 57.67 multiplied with sin 55. This one F2 is 43.18 multiplied with cos 40, and then 43.18 multiplied with sin 40. Okay, so you get that answer. Right. Now let's look at this exercise. A boat leaves a port on heading of 40 degrees with the automatic pilot. Okay. Set for 12 knots. So it's about this way. On this particular day, there is 6 knot current with a heading of 75. Okay. So now we have heading 40 degrees. Okay, and then there's a current of 12 set for the, and then okay, this one 12 knot, this is the unit, and then this one is 6 knot. Okay, and then one is 40 degrees, another one 75. Okay, sketch and level the vector to represent the intended path and both the current and the resultant path both with the effect of the current. So it will be like this way, and then this way. So you can make another one here, and the resultant will be in here. This one parallel with this. Alright, calculate the velocity of the boat will actually travel due to the effect of the current. Alright, so component of the boat velocity, and we have the boat velocity. I put it as a VB lah. VB, boat velocity. So we have 12 cos 40 degrees, and then 12 sine 40 degrees. Alright, so here you will get 9.192 and then 7.714. And then for VCX, VC, which is the current velocity, you will have 6 cos 75 and then 6 sine 75. And you will have here, which is about 1.553 and then 5.795. Alright, so the VRX, I mean the resultant velocity with respect to the X direction. So you have 9.192 plus 1.553, you will have about 10.4745, and then the resultant in terms of direction Y, you will have 7.714 plus 5.795, which is 13.4509 knots. Alright, so the total speed will be the VRX squared plus VRY squared root FT. So you will get about 17.28 knots. And then the angle, I put it here, tangent inverse the Y versus the X, which is 13.509 divided by 10.745. So you get 51.5 degree. Okay. Alright, and then for the second situation, which is the same situation, which is now we have the plane leave the airport on heading 45 degrees, travel 400 mph, and the wind is blowing at the heading 135 degree at a speed 40. So again, same, the first one you find the velocity of the plane in the X and Y direction, and then you find the velocity of the wind in X and Y direction. Okay, so and then after that, same step, and then you total up the resultant based on this formula, and after that you find the angle VR in terms of V resultant in terms of I divided by Vx, and then you tangent inverse it. Okay, so you can try this one on your own. You will get that the value is 406 mph, and also the theta here will be 49.4. And then I saw for the this one, find the magnitude and component of vector f1 and f2. Okay, I think this one is quite the same as previously. You just find the y component, you add up f1 sine theta, sine theta, and then f2 sine theta for the y component, the x component f1 cos theta but then negative direction, and then this one f2 cos theta. So here and here the angle will be the same, here and here the angle will be the same, because this is two parallel line, and then angle here and angle here will be 30 degrees. Right. You need to make sure that also the this way, meaning that f1 sine theta and f2 sine theta is equivalent to the 100 times 9.81, which is the direction downward. Okay, right, you can try that one on your own. Alright, I continue with the another application, which is you can calculate the work done by using the dot product, where you have a two vector, and you dot product it, you will get a scalar, and this dot product can be used to calculate the work done on that particular situation. For example, like this, we have a box here, with that being applied with the constant force F here, during and then when the constant force is pulling in this direction, the resultant of it, there is the displacement of D in this direction. So this is how it looks like. We can calculate the work done here by computing the dot product of the force, the constant force that being applied to that object to move the object, with the displacement of the resultant force. So that is the work done particularly in x direction. Also, there's also force perpendicular to the motion that do not work, which is like this. There's a gravity here, and also in terms of the opposite direction of the force coming from the gravity. When an object is displaced horizontally on the flat table, the normal force or N and the gravitational force, which is Fg, do not work, since the cos theta here will be 90 degrees. So if you get cos theta 90 degree, it will be 0. So Fd cos theta, then it will be cos theta will be 0, and then Fd will be 0. So that it means that there's no work done in that particular area. Perpendicular to that object. Okay. Alright, this example, if we have the force of 40 Newton and the D, due to that, it has the D of 3 meters, and the angle is cos theta. So the work done by this Fn is by this F and movement of the D is given as dot product F dot D, which is Fd cos theta, which is 40 times 3 and then cos 60. So you get 60 joule. Alright, let's look at this example. How much the work done to slide a crate 20 meter along the loading dock by pulling it with the force 200 Newton. Force is 200 Newton, and the distance is 20, and the angle is 30. So the work done is actually this one meter, Fd cos theta. So Fd cos theta, so it will be 200 times 20 and then cos 30 degrees. So it will be 3464 joule. And then for the second part, this 30 degrees, 30 kg box is placed on 10 m ramp up, like this. Alright, this is 30 kg. Okay. 10 meter in an incline 20 degrees, 23 degrees. Calculate the work done. So here we can have the F in terms of the gravity here, which is 30 times 9.81, and you will get about 294 Newton. And then the F in this direction, which is F gravity sine theta. Okay, you will get 294 times sine 23 degrees. Okay, so you get the answer here is about 114.84, and then the displacement just now stated as 10 meter. So the work done will be 1148 joule, multiply with the 10 meter just now. So 114.8, correct lah, 114.8. This one 114.8 times 10 meter, you get 1148.4 joule. Okay. Alright. Now we look into the cross product. Just now the work done is dot product, and now we look into the torque, which is the output coming from the cross product. When we turn a ball by applying a force F to a wrench like this, in this figure, we've produced a torque. The torque is actually the cross product. The torque is the torque vector point in the direction of the axis of the boat according to the right hand rule. So the rotation is clockwise, and the torque is the direction of your thumb. If you move your thumb, the movement is actually your fingers, the rest of your fingers, and then the torque direction is your thumb. And the torque vector is given as RF, the magnitude of R, meaning the length of you pulling the torque vector here, and then magnitude of the force that being applied, sine theta, because this is the cross product. Alright, for example like this, find the magnitude of the torque generated by the force, this force at the pivot point P in figure 5.4. So this is 3 feet bar, and then the force that being applied is 20 pound. So the PQ cross F, so it is PQ, the magnitude of PQ multiply with magnitude of F, sine 70 degrees, because this is a cross product. So you get 3 multiplied by 20, sine 70, 0.94, you get this answer. Okay, alright, and then alright, we do have a triple scala of box product. The product is called triple scala product. This is in week 4 notes. As you can see, the formula is given as U cross V dot with vector W, meaning that U cross V, you take the magnitude of U cross V, and then magnitude of W cos theta. The absolute value of this product is the volume of parallelogram side bosses, determined by U vector U, V, and W. U, V, and W. So U, V, you cross product the plane at the bottom part here, U cross V, and then you dot product with the W cos theta. Alright, so this is how it looks like using 3x3 matrix. And let's look at the example here. Find the volume of the box, which is parallel pipette, determined by vector U, V, and W given in this. Vector U is 1, 2, and -1, and then vector V is -2, 0, and 3k, and vector W is 0, 7, and -4. So you do cross product dot vector W. So 1 to 1 from here, and then this is vector v, and the middle one is vector 0, 7, negative 4. So you can click calculator using your calculator to find the matrix determinant of it, and you will get the answer is 33. But the volume is magnitude only. Volume is only magnitude, and it's not it's a scalar thing. It's not a vector. So that's why it become 23 units cube. So you can do the rest for this. So same like u times v dot w. So you will get u is 200, 020, and then 002. You click calculator, you find the answer, and you can do for the rest. Alright. Alright, we continue with the next topic, which is interpretation of directional derivative and gradient. So directional derivative and gradient is very, very much important when you want to find the slope of the equation, and you want to find the meeting point or the coordinate of the tangent that touches the surface of any plane or any surface. So look at this figure. The slope of the curve C, the curve C here, the curve C is the blue color, at P naught, at this point, is called the DUF, directional derivative, which is generalized to partial derivative. So the concept is similar as what we covered in partial derivative class. We can now ask the rate of change of function f in any direction u, not just in the direction of I and j only, okay? Because now it's three-dimensional. So for physical interpretation of directional derivative, suppose we have the function of fxy is the temperature at each point x and y over the region of the plane. Then fx naught y naught is the temperature at the point p naught x naught y naught, and directional derivative is the instantaneous rate of change of the temperature p naught stepping off in the direction u. So the property of directional derivative is as the function increase most rapidly when cos theta equivalent to 1 and when theta equivalent to 0, and u is the direction of del f. That is, each point p in its domain increase with the rate of change of that gradient. Actually, it's kind of complicated to explain in a way like that. Directional derivative meaning that if one point, if any plane or line touches any surface, any curve line, and you can find the directional derivative of any point of that plane touches the surface. Any point here, any point on this plane touches that surface, you can find the directional derivative of it. Using the formula like this. Directional derivative of that function with respect to the angle that touches the curve. And if it's orthogonal to the gradient, and when the gradient is not equivalent to 0, we can say that del f dot 0 equivalent to 0. Okay, for example like this, if we have that one function, this function is the curve just now that I mentioned, the curve just now at p naught 1, 1, 0 in the direction of this vector. So the vector here is the direction. Find the derivative of it. Okay, so the direction of the vector b, the vector v, we can find the directional vector or vector position, okay, where we find the v divided by magnitude. Okay, so this one is 2, -3 and 6, and then the magnitude will be 2 squared plus -3 squared plus 6 squared. So 2, 3, -3 and 6 divided by sorry, I forgot this one, 7. Okay, right, this is what you get from here. And now we compute the partial derivative of that p at p naught. So meaning that you do del f del x, del f del y, del f del z. And then you replace the value at p naught. P naught just now given as 110, 110, so you get 2, -2 and -1. So the gradient is the vector, which is 2, -2 and then -1. The derivative of of f at p naught in the direction of v is therefore directional. This is what we call directional derivative, which is the gradient just now, the gradient vector dot product. This is the gradient vector dot product with the direction of v, unit vector here, directional vector, or unit vector here. Okay. Okay. So the second question asks, in what direction does f change most rapidly at p naught, and what are the rate of change in this direction? So the function increases most rapidly in the direction of this. So do you know, how do you know that? Because that is the gradient of the rate of the gradient is also the rate of changes. So this is the rate of the changes, and the decrease most rapidly in the negative f direction, negative nabla f. The rate of changes in the direction are respectively given as the magnitude of it, and the negative magnitude of it, which is 3 and -3. Okay. Okay. Next we have the curve that surrounded by the temperature given as 100 minus x squared minus y squared minus z squared, and the f x y z is defined to be the gradient of t, meaning that the gradient of t is the changes of t over time lah. Find the vector field f. So now this is the scalar, and this is the equation that consists of 3 dimension x, y and z. Now we find the gradient field. When we find the gradient of f, we will get the vector. That's the concept that in the week 3. So the how to find the gradient of f? You just do del f x. You find the fx, fy and fz. So meaning that you take partial derivative of the del f del x, which is fx, which is negative 2x. Fy del f del y, negative 2y, and then fz, negative 2z. Okay, so delta t is actually fxi plus fyj plus fzk. This is all partial derivative. Okay, so you get -2, -2 and -2. Okay. Alright, let's look at this example. Not example, exercise. Sorry. Okay, for the first part, find the direction in which the function increase or decrease most rapidly at p naught. Then find the derivative of the function in this direction. Okay. Again, we need to find the gradient actually, because we want to know the rate of the function increase or decrease. So you need to find nabla the gradient of f, which is del f del x, del f del y, del f del z. Okay. Alright. So from the first one, you will get 1 over x plus 1 over z for the I direction, and then 1 over x plus 1 over z in j direction, and then 1 over y, 1 over x in k direction. Okay. Okay, now we need to find at P111. So delta f, nabla f 111 is given as, you replace 1 over 1, 1 over 1, 1 plus 1, 2, 1 plus 1, 2, 1 plus 1, 2. Okay, so you get 2, 2, 2 here. Okay. Alright, so the direction of maximum increase, del f is, this vector, I put it as vector V. So the maximum increase is positive, this one, 2, 2, 2, 2. The negative, the maximum decrease will be in the opposite direction, which is negative 2, negative 2, negative 2. Alright. And you can find the magnitude of it, and the magnitude of derivative in maximum, you will get, the VF, like this, V, and then here negative V. Okay. So you get here 2 cert 3, another one is negative 2 cert 3. Okay. Alright, you do the rest for B and C. I put down here, in case you want to cross check. You need to do nabla G here, and then for the first part you will get e to the power of y, and then x e y, and then 2z. Please try on your own. And then at p naught, which is equivalent to 1 or ln 2, ln 2 and then half. So delta g at p naught, you will get 2 to 1 later. And then direction of maximum increase is V equivalent to 2 to 1, and then negative V is equivalent negative 2, negative 2, negative 1. Okay. And G here will be 2 squared plus 2 squared plus 1 equivalent to 3, and then the negative lambda G maximum degrees is negative 3. Alright, for the C part, you will get nabla F equivalent to 1, negative 5, 1, negative 1, and then the derivative in the direction of maximum increase of 3 cert 3. Okay. And minimum decrease, you can check, negative 3 cert 3. Right. Next we look into the gradient, tangent and normal to all curve. This one we already covered actually during the discussion in week 3 and week 4. Now we look into the example in the scenario setting where we have to find the equation of tangent to an eclipse as shown in here. So we have this eclipse. The function of this eclipse is x squared over 4 plus y squared equivalent to 2, and then there's a one tangent line that touches this point. This point is this point. Alright, so we need to find the equation of tangent. First, we need to find the nabla at that point. So you find del f x del y and then del f del y. So you will get that this one is x over 2, and then this one equivalent to 2y. So this one you get this one. And then the tangent line will be like x plus 2. This is negative x naught. So that's why negative will become positive, y minus y naught. And then the 1 and 2 coming from here, negative 1 and 2 coming from here. Equation of tangent line. So you get this tangent line. Alright. Next example is now the difference is this one to D. Now you have a 3D curve. You have the tangent plane as shown in here. And that tangent plane touches the normal line here, touches this point P0, 1, 2 and 4. So same goes. It's just that now you have to find del f del x, del f del y, and then del f del z. Like, here you will have a 2 from here. Here you will have 4. No, 2y, 2x, 2y, and then 1. Okay, at point 1 to 4, that's why you replace 2 times 1, 2, 2 times 2, 4, and then 1 is 1 lah. Alright, so 2, 4, and 1. This one is the P naught. P naught. P naught. Okay, so then you have this equation of tangent plane. The normal line is the normal line to the surface using the same formula. You can get this one. This one is just changing from the Cartesian format to the normal format. Okay, this one in week 2. In week 3. You can do it on your own to find the surface on that. Okay, the tangent plane of that surface. Alright, and then we look into the divergence angle. The divergence angle is covered in week 3. But the engineering application is discussed in this. Normally, we define the divergence and also the curl in terms of the normally when we have the vector field, when we are rotating the flow. Meaning that it can be, the flow can be air, can be water, and so on. Okay. The direction is depend on the right hand rule. The movement of the curl is depend on that right hand rule, and the direction of the normal line is following your thumb. This one is not that not that important. You can read, not like to say not important, but then is for you to understand that how the divergence is working and also how the curl is working. But the same concept is actually applied in week 3 notes, where the formula, if I may recall back, the formula of the formula of the gradient is nabla like this, where you have del x, del y, and then del z, and then the directional derivative you find, and then the divergent you will get a scalar. Divergent you will get a scalar, where is the vector v1 del x plus del v2 del y plus del v3 del z. Okay, that one is for the gradient, and the curl will be the cross product, nabla dot with the vector. Okay, and you will get again the vector field. That's the example here try to explain actually. It just depending on the shape here is actually coming from the equation from here, whether it's rotation, whirlpool, and so on. But don't worry on this. Normally we don't really ask we don't really ask on the graphical interpretation, rather than we will give a situation and we ask you to determine the gradient and the curl. But you need to understand, if you are determining the changes, the rate of the vector increase or decrease, that is actually gradient vector already. The gradient itself explaining that the changes. Okay, alright. Later, before exam, don't worry, and before test I will do a revision, and so that we can have a look at the topic one by one, the related topic that will come out in the test and then final exam.